Alright, it should be live, I guess. So we'll get to where we're supposed to go. I think we will anyway. Which one do I want? I have to find the right window. I suppose it doesn't matter, so that's the one we're going to end up at eventually. And, but we want Bohm. That's Bell. That's Bell. That's not right. This might not be it. There we go. Okay. All right. So, it's this whole Bell thing is just so convoluted, and it's broken by so much of what they do to language in terms of using these words local. So, local doesn't mean local. Doesn't mean that it has to be really close to you. It just means that it's not going faster than the speed of light, or it's not instantaneous. So if they say it's a local variable, then it's a variable that's not relying on some sort of ESP power, versus a variable that is whatever, superluminal. Even the very idea of having a conversation about influences that aren't slow is just kind of, I'd say, archaic and silly, because we have so much evidence that nothing is able to do that. But regardless, so they give you this idea that's so the regular Copenhagen explanation has in it this idea that somehow the two waves are interfering with each other, this mechanism, and that over distance this would mean that influence to create interference, I guess, would have to be faster than the speed of light. And then this Bohm explanation of pilot wave, which really just says you do the same thing as Copenhagen, do the same thing as magical wave interference, except you just have a little piece of something floating on it somehow, and somehow the piece just lands in one location. So all of the waves do all of the places, go to all the places, but the actual quantum of energy, just goes to some probabilistic thing. It's somehow it knows what it did in the past, and it figures out where it's supposed to go this time. Something like that. I don't know. Somehow it turns out that way. With each permutation, the ball sticks to some other different location in that drawing. But anyway, somehow this fixes the locality problem, because it isn't dependent on faster than light, because it's building up to the location it's going to create or something like that. I have no idea exactly why. But anyway, so this was supposed to be a solution, partial solution to the Bell problem, and the non-local problem, whatever all those problems are. So as you can crudely see in this drawing, in this image, which is on Wikipedia, it's in different places, this is how it works, and it's supposed to be a solution to the two slits, and clearly it's not producing either pattern. So it's neither creating a single slit pattern accurately or a double slit pattern accurately. So it's doing neither one, and yet, because it's creating interference, that's all that matters. So that's how structured and rigorous their application of words, like it's a successful theory. It doesn't have to really do anything like predict actual outcomes. It just has to in some vague way look like it. And therefore it's a perfect match, and therefore it's a perfect solution. So, I shouldn't even have to draw this, but I'll draw it just for the sake of just illustrating the point. Alright, so the slit patterns are in two forms, as I've kind of kept pointing out. You can have the real double slit, and it has certain rules, odd number here, always odd in the center, always a multiple, in the sense that if this is 5, then the nodes will be 3, because basically these are just two overlapping nodes here. Alright, and so this is the perfect let's just call it double slit pattern. If you can do it very well, this is what you can make it look like. So you could have 7 here, you could have 10 here, you could have 15 here, you could have 2 here, you know, I mean 3 or 1. But that's it. That's the double slit pattern done well with open slits, okay? Not infinitesimally small slits. Infinitesimally small slits will not create this complex pattern, this prettier pattern. Okay, so if you do as they recommend, which is break the experiment substantially, yes, you won't get this. If you use infinitesimal slits, you cannot do a double slit experiment and get anything like this pattern. Alright, and then the single slit pattern, so this is 2 slits, which is 4 surfaces. Okay, so let's just understand, when we say 2 slits, we mean 4 surfaces. Okay, and then the single slit pattern, okay, will create this. Alright, and you can have, it's the same rules, I mean, in the sense that you can have more or less. So I could have 70 of these little things. The center one will be double, okay, so we have a 2x in the middle, and you'll get nodes that are half, you know, plus of what's in the center. So I mean, if this is 5 inches, this will be 3. And again, it's just the overlap argument. You just basically what you'll see. So obviously, what they're showing is this, okay, which isn't either one of the patterns. Okay, not either one. Doesn't fit. Single slit doesn't fit double slit. Not the same pattern. And yet they're saying, ah, winner. You know, we did it. So they're saying we did it. We came up with a good explanation. It's missing this and it's missing this. Alright, so that's pretty poor. So as I've explained, the simple solution to the double slit is the photon, a single photon, does not go through 2 slits and interfere with itself. That story is just garbage. Okay, and every time they say they have a single photon in an experiment, you can be suspect for rational reasons, because you can go through the mechanism they're saying they're creating the single photon with and explain all the places where you're not really creating a single photon, you're just breaking photons, creating a bunch of parts you're throwing into the atmosphere, and then you're recombining some of those parts back into a photon. So, you know, it's pretty simple. So as I've pointed out, you can have 2 slits, and the trick is, you know, you have them separated from each other. They just look like 2 slits, okay? All they can do is create this pattern. This one will create it, and this one will create it. And if I bring them closer and closer together, I would just say, yeah, well, this one will be a tiny difference in distance, right? This slit, let's say I bring them closer together. All right. So I draw it. I now have this circumstance. All right. So now I have just 2 openings, okay, and you know, and all it's supposed to be is this pattern plus this pattern, and they're only a millimeter apart. So yeah, one of the patterns would just be overlapping the other pattern a little bit, you know, and that's all there would be. There couldn't possibly be anything else. But that's the trick of it, is that this proves that it's about the surfaces, about the sources. And it proves that what you've really done, okay, when you bring those 2 slits together, is you created 2 different single slits. This slit combines with this slit, and this slit combines with this slit. So instead of having 2 this way, you now have, you know, what's a good way to draw it? You now have this distance, okay, combining with this distance. Alright, and those are your 2 distances now. So instead of just having this distance, you have, you know, this distance and this distance. And those 2 distances are where you draw your vectors from. That's how you figure out your math. You do your surface, you know, math. So the Bohmian explanation has the same silly, okay, 2 waves coming out, 2 waves interfering to create the double slit pattern, when the double slit pattern is basically showing you a very wide opening pattern. That's the little bars, okay, and a very narrow pattern. That's creating the envelope. And that simple explanation works perfectly. You don't need any Copenhagen, you don't need any entanglement, you don't need any wave interference. All you say is that photons go in, they hit surfaces, they get messed up, pieces fly in all directions, and you have a 50-50 chance of putting your photon back together again on the surface. The end. You just do the geometry. So anyway, I mean I can play some videos, maybe we'll get into some of this stuff. It's just that you have to get all the jargon straight. So every time they say a word like local, or every time they say a word, you have to be able to understand what they're really saying with that word. And if you don't know those key words or, secret language they use, you can't really understand what they're talking about. And Bell's argument is really kind of simple. He's basically saying that 1/4 plus 1/4 can't equal 3/8. Yeah, okay. Yeah, that's true. So the experiment comes out with 3/8. Okay. The prediction is 1/4 plus 1/4, so it should be 2/4, 1/2, and it's not. And again, I could make the same argument right now about how they calculate how much energy something has when it's rolling friction. And they basically are saying that there's the same amount of friction no matter how fast you go across the surface, same amount of friction per foot. And I can make the argument, no, it isn't. So yeah, the experimental result's going to be 3/4. That's where half the speed is, at 3/4. Half the speed isn't at half the distance. So it's the same thing, and he's basically saying, well, that's impossible. You can't do that. Those answers can't be consistent. You've broken the rules of probability. Yeah, you got an outrageously wrong answer. So if it's that far off, it can't be true. Yeah, of course. This is not true. The prediction is wrong. Quantum mechanics is wrong. Okay, 1/2 mv squared is wrong. It's a wrong assessment of where energy is going. The fact is that when you're going faster over the surface, you're losing less energy to the surface per foot. Just a fact. So you can go this much distance and lose 50 watts, and then you go the last little distance and you lose 50 watts. So that's the truth of it. It could be understood. I don't need a Bell's inequity to tell me that 3/4 isn't anywhere near 1/2. Yeah, it isn't. That's a wrong answer. Because your science is wrong. Your assumptions about what happens is wrong. Just as this Bohm assumption, okay, that this pattern is the double slit pattern, that assumption, okay, is wrong on so many levels. First, there's not just 2 waves that make the double slit pattern. It's not 2 sources. It's 4 sources. And the second one is this huge giveaway that you got the wrong answer in the middle. There's not a double maxima here. Wrong answer. There's no reason to say anything more than this doesn't work. You don't say it works. You don't say it does everything necessary to solve the problem. It doesn't even create the right pattern. Alright, so that's their science. Alright. So yesterday I did a video, and I'm not too satisfied with an argument I used. Let's see, I don't have that still up, I don't think. So we'll have to live without it. Yeah, there's the video. Alright, arguing this lever thing, and I'm not really satisfied with the explanation I provided, right? Because that's acceleration. And so, I won't go into it in detail. It's this, there should be a better image than that. Yeah, there should be, there's one. This experiment that was done. And again, it has this pendulum on it for no good reason. I think it's just a distraction, so get rid of that, get a regular quick release. But the fact is that the system seemed to have less energy in it, okay, the less weight there was. So if I put 2 1-pounds here, so we have, a 2 mass here, 1 plus 1 plus 1 plus 1, so we have a total of 4. And if we just put 2 single masses further out, somehow this mechanism will move slower. It will, if I'm correct, yes, it will take longer to oscillate, which means it's moving a little slower. So somehow it loses energy. And I would argue that that can't make any sense. So there's obviously a mistake in the experiment somewhere. Somewhere these distances aren't correct. Something's off. But I'll stick with that explanation versus saying it has something to do with how much weight is in gravitational potential, because frankly it can't matter to the oscillation. Theoretically I don't think it can matter. So anyway, just make that a clarification. I'm not too sure of that explanation. I don't like this setup. Okay, it looks like it's got lots of room for some kind of mistake, and I'll leave it at that. So until he disproves Brozo's experiment, until he disproves the, like I said, he draws a lever and explains how it works. This doesn't say anything except they're not the same. Well, technically they should be the same, and the fact that they're a little tiny bit off, 10% or so, which isn't that tiny. But anyway, it's a consistent 10%, meaning that it could be a consistent mistake. But anyway, yeah, so we'll save that for another day. Again, the fact that science doesn't already have all these experiments well documented, is just kind of glaring evidence, like the Eddington experiment never being redone, that they can't deal with the facts. So, redo the Mythbuster experiments, redo these experiments, and prove that they lied, they made a mistake, okay, and that kinetic energy is somehow real. Okay, do any one of these experiments with guns or levers or spaceships to demonstrate that somehow there's all this magical free energy available that doesn't happen because something stops it, some phenomenon stops the conservation of momentum. Because this is really just an argument saying there is no conservation of momentum. And it certainly doesn't provide any analysis of why there's less energy. And if you're going to claim there's less energy, where did it go? Because there can't be less energy. Alright, anyway. So, then I guess we'll go back to this crap. Yeah, we'll play some more of Brian Greene's antics regarding why we should believe the silly relativity theory. Alright, so let me get the chat thing so I can see it. So much to do. Alright, so nothing in there, of course. So, very little participation. So let me see. We want that. Alright. We'll see if this works without me having to fix it, which it probably won't. Ah, it did. Good. I think it did. Let's see. Yeah, it's there. Okay, so I'll move this up. Well, it didn't move. Whoops, wrong one. This one. Yeah, this one goes up here. And then this one I can, since there's nothing in it, I can move it down there. Alright, there. That should work. Alright, so it should pick up where I left off, but we'll see.
Einstein added something to the list. Einstein added to the list of things that would not change, he added the speed of light. This is the surprising new insight of Einstein. Let's see what it means.
So again, it's obviously the fact that light doesn't change, that it's awfully consistent, was already noticed by a lot of people. I mean, I think you could argue it was already in Maxwell's equations, that none of those equations could make any sense over time if the light speed was a variable. It was a constant in the equations, and you wouldn't be able to get coherent answers if there was a variable speed of light. So the answers would be randomly off all the time based on some variability. And then if the variability had really to do with how much distance something was going, that means that the speed of light changed more the faster objects were moving on their own. Yeah, it would really have screwed up those equations. But anyway.
The speed of light is constant, right? That is one of the most famous sentences in all of science.
All right, it's just amazing that that's what he would say. That's what the that getting hit with a I don't know, a tomato in the face hurts more than you think it would, or something. That's the most famous statement in science. I mean, whatever. What goes up comes down. That's a lot more famous, I think.
Speed of light is constant. Now, what does it mean, and why should you care? Well, to get there, let's think about how it is that Einstein came to this idea that the speed of light is constant. It's an interesting history where, over the course of many centuries, many people struggle to
So, I mean, the very idea, right? I mean, I never had a moment in my life where I was in any doubt. I mean, there was nothing about any circumstance that screamed that somehow the radio wave could be moving at variable speeds or something. None of that could possibly make any sense. Every piece, every element of the wave has to move very consistently and has to go thousands and millions of miles, right? We have to, send signals. How could the signal possibly change, especially internally? So obviously it seemed like, oh yeah, it's pretty damn consistent shit. Whatever it is, it works really reliably.
Understand light. And perhaps a good place to pick it up is in the 1600s to the 1800s, when a whole
which is a huge span of, in the change of how physics was understood. So it's almost before the sun was in the solar system to 1/2 mv squared.
Group of physicists spent a lot of time, put a lot of effort into trying to measure the speed of light, and they did a pretty good job. Romer, Huygens, Bradley, Foucault, Foucault.
Right, so this was all happening at the same time Newton was alive. So again, they keep implying that somehow Newton didn't even give it a thought, or somehow Newton automatically said everything moves instantaneous or something. So this was already an open question about how fast all these forces, the invisible stuff, gravity and light, moved.
These guys, some of whom had very long hair, made increasingly precise measurements.
Well, yeah, just to understand, Huygens had a preposterous wig, okay? And he called himself von Huygens. I mean, no, that was Leibniz, von Leibniz. So Leibniz had an even more outrageous wig. Like it's almost like they were that trivial. Bigger the wig, bigger, you're more important.
Of the speed of light. With modern updatings, we now know that the speed of light is 671 million miles per hour. If you like those units, it's 300 million meters per second, or a little bit more precisely, it's 299,792,458 meters per second.
Right, preposterous, really, when you think of it. Just, wow, that's really fast. It's a lot of distance in a second.
But we will round that off to 300 million meters per second for the most part. So that was good. People understood the speed of light. But even so, physicists lacked an understanding of what light actually was. And that's when two physicists, Michael Faraday and James Clerk Maxwell.
Right, and what they did was they discovered the speed of induction, and that ends up being the same speed as light, because they're going to say that light is some sort of inductive process. Okay, it requires two fields. Like you have to make it out of something, and really all you're doing is making it out of the motion of electrons. But whatever, we'll get to that.
Who, through experiments, mostly Faraday, through theorizing, mostly Maxwell, they realized something quite amazing, because they studied electromagnetic waves. They studied ripples in an electromagnetic.
To tell you the truth, I don't know what Faraday thought the things were made out of, but it's, just to give context, Faraday's conception of how matter absorbed the energy was to create a bunch of gears inside the stuff with little idler pulleys to make it go left and right, and so that fixes the clockwise counterclockwise problem and all kinds of. So let's just understand they really didn't have a very good conception of what this stuff was. Whether you called it a corpuscle or a wave, it wasn't a very, they couldn't draw you a picture that would make any sense.
Field and came to a stunning conclusion. So Maxwell did this mathematically based upon the experimental results of Faraday, and roughly speaking, what Maxwell ultimately concluded from the equations, from the math, was that an electron...
Okay, so yes, and the magnetic portion is much smaller than the electro portion, but they don't draw it that way. Okay, so, you know, and it's, what is this? So this is just a representation of you turning on and off an electric field and what you would call a magnetic field, whatever the hell that would be. And really all you're doing is turning on and off an electron. You're pushing energy, compressing energy, you know, reflections. So basically the idea would be as if I could theoretically move really, really fast towards the camera and then away from the camera, I could turn myself into bright, dull, bright, dull. I could make myself look brighter and less bright because you would get more reflected energy as I move forward and less reflected energy as I moved away. That's all you're seeing is a frequency. You're just seeing something moving forward and back, okay? So we don't need to do all this other stuff to account for the frequency. And that's all you're trying to do is account for the frequency. Whether it's transverse or doing any of this, two different kinds of fields, all of that is their addition. That doesn't have anything to do with the actual observed condition, which is a frequency. That's the only thing you know is happening. You know a frequency is going from one place to another. You don't know any of this.
Magnetic disturbance always travels at a particular speed, regardless of the wavelength, which is the distance.
So you could just argue that whatever it's admitting, okay, is exactly what we understand it to be. It's a reflection of the environment. The environment's full of light. Okay, light I can see and light I can't see. It's full of this stuff coming at me, hitting me at a frequency. I'm vibrating at a frequency, so I'm going to obviously change the frequency of the stuff hitting me. Not that complicated.
Distance between one crest and another. And remarkably, the speed that he found for electromagnetic waves, again, independent of whether they have a very long wavelength.
So, yeah, just to understand, very long, like miles long. In the case of a radio wave, we have to believe that something is miles long doing whatever this is. Miles of whatever this is. Whatever this is, it's being detailed. Little pieces, something, yo, it's this intense, it's this intense, it's this. All of that detail has to, all that information has to be in something miles long. When the simple solution is, no, there's a mile between the cannonball. 1 mile of distance between them. You're shooting cannonballs, you shoot them at this regular rate, and there ends up being a mile of distance between the cannonballs. It's so much simpler an explanation, and there's no facts that prove it to be wrong.
Or if, for instance, they have a much shorter wavelength, like this fella coming in here, he found in the equations that the speed of those electromagnetic disturbances would always be equal to a particular number, and that number turned out to be...
So I mean, these disturbances at that time that they were talking about, Faraday was measuring, was induction. So again, it's not... They're measuring how much you can jiggle a magnet and how fast it influences, you know, how much lag there is in the function. So what the medium you're using to communicate the movement, how long it takes it to get to the thing receiving it. And so they measured the speed of induction. They didn't measure the speed of light directly, visible light. They measured the speed of invisible radio.
671 million miles per hour, or 300 million meters per second. So this was a stunning insight. And again, if you haven't studied electromagnetism, it doesn't matter. All that matters here is that Maxwell had these equations, and from the equations out came, from a calculation, a speed that was equal to the speed of light. What was Maxwell?
Right. So the simple conclusion is that all these forces are the same thing. It's the same stuff. All the invisible stuff is moving really fast. That's the simple solution. So anything that moves, something else, every time you see matter move, gravity, magnets, electricity, explosions, and there's a piece of the explosion moving very, very fast, that stuff is force. And then you could go all the way to the radiation experiments where you start breaking it down into the gamma radiation versus the alpha and the beta.
To conclude, well, naturally, he said, if the speed of the electromagnetic disturbances is equal to the speed of light, then light itself must be an electromagnetic disturbance.
So kind of a backward way of doing it, where you could do it just the opposite way and just make the opposite conclusion. Say if light's corpuscles moving through space, then that's what magnetism and electricity is. So you could go both ways. But the point is, it shouldn't have been the speed of light. It should have been now stated that what we understand is this is the speed of everything that is in the form of force. So it's the speed of force.
It must be an electromagnetic wave. That's
the speed of ether, even. They could have said that and it would have made more sense.
That was a great step forward. Now we had an understanding of what light actually is. But even with the progress that represented, it still raised a profound mystery. And that mystery is this. As we described before, whenever you talk about speed, you need to say an object has this speed relative to that object. You need to state things in that manner for speed to even have any meaning, right? But when it comes to the equations that Maxwell was studying, they didn't specify what speed, 671 million miles per hour, was relative to.
But they need to, because they're basically just saying, just draw a mile, make your ruler of distance. So I make a ruler that's 1 foot, and now I can put the 1 foot anywhere. I can put it under the water, I can put it in the air, I can put it in empty space, I can put it inside the moon, I can put the 1 foot anywhere. So just make a 1 meter stick. All right, and I'll tell you how many of those end-to-end are, So they don't need to do any relative comparison besides just say we've established what a distance is. This is the distance from one end to the other, and now I'll just tell you how many of those distances it is. And I don't care where it is in space. So they were still in real three-dimensional space at this time.
Right? So if you have sound waves, the speed of sound is relative to the still air. If you've got water waves, the speed of the water wave is relative to the still water.
It's really not. It's really a measurement of how many units of a set unit it's traveling. So, it's the statement about the condition in the sense that, yes, it's always going to be relative. You're saying that this thing is moving in the environment relative to other things in the environment. So yeah, we always establish the Earth isn't moving, it's not rotating and it's not doing all this extra stuff and flying through space in all these directions. So we're just making a relative comparison. But you can't turn that into an absolute statement either way. It's just understanding it's this many units.
What was the thing relative to the speed of light was being calculated? Nothing seemed apparent. So physicists dealt with this mystery by making up an answer. They said maybe there is something called the ether filling space, and when you talk...
No, that's not why they invented the ether. They needed a medium to be transmitting this stuff because they couldn't conceive of it as being cannonballs or being things with perpetual momentum for whatever reason. I mean, I find that totally conceivable. But they couldn't conceive of it, so they needed some kind of dominoes to transmit the momentum. So that's why the ether exists. It doesn't exist because they need something to make a relative comparison to. So, and so now he's just trying to destroy the ether because the ether implies that space is full of actual stuff that has actual substance and distance, and they have to be able to turn space into something they can contract and expand. And they couldn't explain how you expand or contract something. So they have to turn it back into nothing and then pretend nothing expands and contracts. It doesn't make any sense.
About the speed of light, you're talking about the speed of this electromagnetic wave relative to the ether. Experiments were done to try to find the ether, and to make a long story short, no evidence for the ether whatsoever.
So it's not like whatsoever. That's really hard to do, the experiments, frankly. And you have to have a ton of assumptions built in about how you can detect motion. So if our motion is changing every millisecond, into all kinds of directions because we're being pulled upon based on all kinds of different influences in the universe. And the influence isn't that Alpha Centauri doesn't influence us with like in some kind of proportional way to distance, in the sense of only over time. So we might only get hit with 5 photons per hour from some location in space. But in the very second, the very millisecond that we actually receive a photon, it's really, really powerful. It's a real photon. It's a whole photon. So it's not like over time we get a little tiny bit of influence every single millisecond. No, we get a giant clump of influence, and then no influence for a long time, and then a giant clump of influence, and then no influence. So what's happening to us is we're actually being jerked around, but over time all the jerks add up to nothing. But at any one moment we can be going very fast this way, or very fast that way, or very fast any one of those directions, because of the influences of all these things hitting us. But we're over time not getting anywhere, because the next minute we'll go very fast the opposite direction. So that's why we can't sit there and make a relative comparison to us, because we're constantly moving very fast in some direction. If we look at us at any millisecond, we're moving really fast in a direction, but over time we're not going anywhere. So those two things are the contradiction that you're trying to resolve for, is that you can't make a relative comparison to a material thing, because the material thing isn't just going this way or just going that way. It's jerking around the whole time it's going there. The whole time it's going there, it's doing a lot of other motion.
Oh, the puzzle remained. This is where the genius of Einstein comes into the story. Because Einstein had this uncanny ability to look at something that everybody else had been staring at and see it in a new way. And Einstein said, look, if the equations are saying that the speed of light is 600...
I don't know. I mean, when you kind of look at it, frankly, I mean, there's so many things that are just glaring, and you're saying, okay, so he saw some of these things that should have been added up. Maybe you could make that argument about Brownian motion. It was already there to be grabbed, or the photoelectric effect, already there to be grabbed, and nobody grabbed it. And I would argue that sitting there glaring to be grabbed was the notion that, what is this 1/2 mv squared stuff? It doesn't make any sense. Every single time you conserve the momentum, which you have to do, and you move energy from big things to little things, you make free energy, and every time you move energy from little things to big things, you lose a tremendous amount of energy. How can that make any sense? How can a 5-ton train going 10 miles an hour have twice as much energy as a 10-ton train going 5 miles an hour? Doesn't make any sense.
71 million miles per hour, but the equations are not specifying what that speed is relative to. Maybe that's because you don't need to specify anything. Einstein said the speed of light is 671 million miles per hour relative to anything, so long as it is traveling through.
So again, the real point of the real value of what Einstein's saying is that if you want to get rid of all the jitter in the universe, so let's just find something that's not jittering. Light. Light is not jittering. It just moves in one direction. It's elemental, so it can't have an influence. It can't be going this way at 50 miles an hour and going this way at 100 miles an hour. An electron can, or a proton can, and every other compound pile of matter can have more than one velocity. So I throw a baseball, it ends up having more than one velocity. It's getting pushed down by gravity, and it's going forward with the velocity I throw it at. So it has more than one velocity. Photons can't do that. So they're the quiet thing. So the fastest thing, it turns out, in the universe, the little bit of force, is really the quiet thing, in the sense it can't jitter. So if you can find one, it will be perfectly quiet, although it's going to be moving very fast in one direction. It's quiet in all the other directions. So there, light can be used as a reference. Where everything else is useless, light is perfectly quiet.
Through empty space. Now, this is a strange idea. It is a maverick idea. You might say it's a crazy idea because we are unused to any speed that isn't relative. We are unused to any speed that, for instance, can't be changed by running toward it or away from it. But that is...
All right, so it does get changed by running toward or away from it, in the sense that you can't measure it over the number of distances to you, because you're shortening the distance or increasing the distance. So it will get to you faster or slower over more time, depending on whether you're going towards it or away from it. But you're not changing how fast it's moving. So yes, an elephant moving 50 miles an hour towards me, if I run towards the elephant, the impact is going to have more energy than if I'm running away from the elephant. Those facts are still facts, and they're still facts for light. Except the energy part. You can't run away from its momentum.
what Einstein was saying. So let me give you just a little visual example of what this constant speed of light, this fact that Einstein was saying that you don't need to specify the reference for the speed of light, it is just a number, a law of physics. Here is what that would imply. So imagine, we have George and Gracie out there again. Gracie has a meter that can measure the speed of light. When she's standing still, George fires his laser beam, and she gets 300 million meters per second. But now let's change things just a little bit, and imagine that Gracie runs away. You would think the speed should be less because she's running away, but no.
Yeah, well, obviously, again, the fact is the light will take longer to get to her. That's going to be a fact. So you can say it's the same speed, but frankly, you're going to be arguing that, it can't, it didn't get to you at the time it would have gotten to you if you weren't moving away from it. But yes, the electron the photon hits is always getting hit by things going the speed of light in all directions. So how to put that? So yeah, I mean, it's still going, if it's going very fast in a direction, electrons moving very fast in a direction, the photon can't add more energy if it's already going nearly the same speed, so it can't push it much faster. That's why matter can't go faster than the force, is because the force is what's pushing the matter. You can't push it faster than the pushers can push. So yes, it won't add energy if you're going very fast. If you're going very slow, it's still going to add most of its energy, 280, 250, it's still going to be a huge amount of extra energy.
Einstein would say it's still 300 million meters per second. It is a constant. It is a law of nature that the speed of light is that number relative to anything.
All right, so they can't do this experiment because we can't go nearly fast enough to create enough difference in that number to even measure it. So, you go 20,000 miles an hour, you're still not doing nearly enough speed to be able to make this calculation that somehow you've lowered the impact of the photons hitting you. You can't measure the energy difference. It's not enough.
Similarly, if Gracie were to run toward George, you'd think the speed would go up because she's running toward the oncoming laser beam. No, 300 million meters per second again. And the same thing would hold true if it's not Gracie that's running.
Right. So and then they also know that the fact is the frequency increases and decreases with that motion, and the frequency ends up being what they consider the energy. So it's this, the same point is made, is that, well, all right, you didn't change the speed, okay, but you're certainly changing the amount of the photon that you're getting, how much photon per second you're changing.
But George, so the source, if the source is running, you think the speed should be a little bit bigger, 300 million meters per second, not 1 iota bigger. And similarly, if George were to be running away, you would think that the speed she should measure should be smaller than 300 million meters per second, but it remains, according to Einstein, the same fixed.
Right, so according to Einstein, but not measured by us, not proven. So we're just saying, okay, that's a fact. Okay, and I would argue it's true that if she had a distance of 1 meter and the photon hits her, she's not going to change how fast. Well, she is, frankly. The surfaces are going to actually move past the photon at a different rate, so she is going to measure it differently. But you didn't change the light, you just changed how she's measuring it. By moving the measuring device is now broken. You can't measure with a device that's moving. I mean, that's the real problem with this thought experiment. You can't move the measuring. You can't move the ruler and then take your measurement with a moving ruler.
Number, a constant, 300 million meters per second. Now, if this is true, right? This is Einstein's idea. If it's true, it's telling us, as we mentioned before.
So again, I would agree that it's true, that you never change light. You can't break it. You can't get the perspective. It doesn't matter where I stand. Light will always move to me, okay, from any distance, from any place at exactly the same speed. So if I just stay where I am and I take 5 things and have them in different places, different distances from me, the light will move the same speed from all the things all the time. And it just doesn't make any difference. And then when I put material substances in the way of the light, well, then that's another question about how fast the light can get from point A to point B, because it's not going to take a straight path anymore. So in empty space, it's going to move a straight line path. Now the other question is does it hit anything on its way and get scattered and have its frequency changed? Yeah, that happens.
That speed has some very unusual properties when you're talking about speeds that are very fast, near the speed of light. 300 million meters per second, or 671 million miles per hour, is very fast, fast enough to go around the Earth 7 times in a single second. But Einstein is saying, at those speeds, you begin to reveal a feature of nature that you...
All right, well, yeah. So the feature of nature, I'm going to just argue that I think the real feature of nature is to recognize that the universe is made out of 2 things, matter and force. The little force bits are moving the speed of light. They have all the momentum. They never stop. And the matter bits are just pushed around by them. They collect them. And when you collect them, you move some lesser speed because you have a heavier mass. So a little thing going very fast hits you. It sticks to you and makes you move very slow in the direction it was moving, until something comes the other way and releases that energy back to the environment. But basically, all the matter that's moving is absorbing force to move. The force is now occupied pushing the matter. And if you put the force back into the environment, then the environment will have more energy. So you're really just changing how much energy is involved moving matter versus how much energy is free to move matter.
would not anticipate based upon footballs or hand grenades or any of the ordinary objects of everyday experience. So if it's true, if speed has these weird features when you're talking about...
All right, so they're completely intuitive and sensible features, frankly, right? I don't find it anything weird to say there's something moving at a constant speed. I mean, that is not a weird idea.
Speed near the speed of light, then that would mean that space and time, because speed, distance over duration, space over time, it would mean that space and time have weird features. That's why this is such a critical...
So again, they're just measurements, and space is distance, okay, and time is time, frankly. I mean, you can't use some other word for it. There's no analogy for a time. There's no similar thing anywhere in the universe. So yeah, time is made out of time.
Critical idea, but of course the essential question is it right? Is the speed of light actually constant?
All right, so this is how could you test? All right, and so all the simple tests, light's going to pass, and then you can do these trickier tests, where you start pushing it through a medium, and then you get all kinds of wait a minute, doesn't get through the medium at the speed of light, so therefore it's moving slower? Or do you kind of recognize that no, it's moving the same speed, it's just doing it by ricocheting through the substance?
We care about the speed of light being constant because speed, again, is a measure of space per time. So if speed does something weird, then that must mean, as we've emphasized already, that space and time must be doing something weird too. And
okay, said it again. And all the weirdness is you're saying there's a certain amount of distance, and the fastest thing in the universe moves that distance at a consistent rate. Not all that weird.
And in this section, we're going to describe one of the most startling implications of the constant nature of light speed, which is that there is no universal agreement on what things happen at the same time. That's where we're going. Now, to get...
All right, so they're going to go to a place that just seems so... I mean, come on, it's almost like this shouldn't even fool grammar school kids. I mean, here I have two things, explosions. And so these two things, a black pen and a white pen, let's just say, explode. And they're going to get ink on you. And you just say to the kid, well, you're standing here. What's going to happen? Well, they're going to say, yeah, I'm going to be mostly white, a lot less black. And I'm standing over here, right? Exactly the opposite. I mean, that's not too hard to figure out, right? I didn't change the explosions any, right? I can just pick a location and I can change how much I'm going to be influenced by one or the other. Because, yeah, the influence over distance is reduced, both in how long it takes to get to you and how much of it's going to hit you. So why should I think these things change, the explosions change, because I stand in a different location to look at them, to sense their consequence, to feel their whatever. So whether it's two supernovas or whatever, it doesn't matter what the two events are. They are simultaneous, and you can't break that. You can't change that fact, by changing where you're standing. So this is another observer, subject, where they have all this observer problem in quantum mechanics, and here they have another observer problem in relativity, where somehow they think the observer gets to decide. And it's just, frankly, it's pooing your pants. I mean, this is really a big this is 2 + 2 = 7. This is really dumb.
Let's start with the basic intuitive understanding of time, right? So over the course of many centuries, we humans have gotten pretty good at learning how to measure time. We have developed all sorts of clocks that through the ages have gotten better and better and better at measuring the time interval between one event and
right. There's all kinds of devices, and you can break them in all kinds of ways, right? So it's that simple, And so we got to like the quartz crystal kind of thing, and that was a really good clock. And then we start using radiation, which maybe that's not such a great idea. Radioactive decay is changed by how much radioactive material you're next to. So if you're in a more radioactive environment, the clock will tick faster, So it's it's subject to easy default, either easy defects.
Another with absolutely astounding accuracy. Now, having said that, we have still struggled for ages to really understand what time itself actually is. We don't yet have an answer to that question, but we do have certain basic understanding of the properties of time. For instance, we all agree that clocks that are properly functioning and properly set, all of those clocks will tick off time at the same rate, so they will all be in sync with one another. They will all agree with one another.
Well, I don't even know what that means, but I mean, they're all dependent on some emergent mechanical event that's taking place because of how fast electrons and protons are moving inside of atoms. So the motion of the electrons and protons being caused by the force is what you're really measuring. So you can't measure the force itself, so you have to measure the stuff that's moving, and you pretty much are just seeking to find a way where the force always moves the matter in a very consistent way. You're doing the same thing. You're rolling the same ball into the same pins kind of thing, so you can have a reliable result.
We also generally agree that individuals that are measuring the duration of an event with properly functioning clocks will get the same answer. We all agree on how long it takes for something to happen, and we all agree, generally speaking, on what things happen at the same moment, right? Those are the basic features of time as we experience time in everyday life. Here is the thing. The constant nature of light speed says that all of that is wrong. It tells us that properly functioning, properly set clocks do not generally agree with one another. It tells us that we generally do not all agree on what happens at the same moment in time, and we generally will not all agree on how long it takes for.
All right. So again, it's just crap, right? I mean, the sundial, or the one that goes by the sundial. We can all understand how the guy over there is going to get a different reading than the guy over here because the sun's at a different angle, hitting the thing, creating the shadow. So those clocks are perfectly reliable. I have no reason to doubt the clocks at all. I don't get his point. There's no reason for us to say because light is a constant speed that therefore sundials don't work. They don't work in the wrong location. But do them right, and they work fine.
Something to happen. Now, those are some pretty striking claims. I'm not going to describe all of them right now, but we're going to take on one of them. I want to describe how it is that the constant nature of light speed ensures that different perspectives of individuals that are moving relative to each other will not agree on what events happen at the same time. And to do that, I'm going to frame it.
Will not see the event the same way. So obviously, if you're really close to the event, you're going to see it one way. You're very far away from the event, you won't see it. So this could just be made as an electron-proton argument. But I can't change the electron and the proton, so yeah, I can make the argument that if I... Alright, I don't know. I have to have something bigger. So I have an electron, and we'll say this is a proton behind it. The closer you get to this electron, okay, the fact is I can make the proton disappear. Well, this is a bad example because I'm not there. See, it's almost gone. It's almost gone. Now it's gone. You don't even see it at all, right? So, yeah, depending on where you're standing next to an atom, it can look completely different. In one case, it looks very positive because you're getting a lot of, if I could actually, make the energy so you could see it. And in the other case, it's, it's like if I made this blue and this is red, you could see that it's a really dark purple. And then it's going to get lighter and lighter and lighter, more and more violet the closer I get to you. So yeah, you're seeing something completely different, but this didn't change. This atom did not change. I mean, I don't even know why there would be a conversation, but somehow you're going to change the events, the physical things you're looking at you're looking at them with a messenger that's sent away from them, okay? And so why would I think I can change where the castle is because the messenger has a broken leg? Or, he went to a hotel and, because the messenger took longer to get to me? No.
In the context of a little story. The story goes like this. Imagine that there are two warring nations, forward land and backward land, and they've just come to an agreement. They're ready to sign a treaty, except each president stipulates that he does not want to sign the treaty before the other. So the Secretary General of the United Nations needs to come up with a plan that convinces them that in the procedure that they are going to use, each president will sign at the same moment. Here's the procedure that the Secretary General comes up with. He says, look, we're going to have you both sit at opposite ends of a table. We're going to put a light bulb in the middle. We'll turn on the...
No, what you need to do is just sit there and do the obvious, videotape, right on top of each other. Superimposed video camera images from the same distance.
The light bulb. When the light reaches your eye, you sign the treaty. You're equidistant from the bulb, and therefore it should take the same amount of time for the light to reach you. You should sign simultaneously.
Right, so that's not going to happen because you're going to put them on a train that's moving, or you're going to do some other thing to make the light and the distance between the persons and the light bulb different. So what? You broke the clock. You didn't do anything else. A light clock can be broken by just changing the distance from the surfaces. So you want to make the light seem like it traveled further? Yeah, play a game of just moving the surface away from the light. This isn't a complicated trick.
So here is the setup. The light goes off. The flash goes toward each of the two presidents, hits them, and they sign the treaty, and they are all very, very happy. Good. Now, they are all very happy that this agreement has been reached, and a few months later, they come to another agreement that, again, they want to sign at the same moment, except this time, both presidents want to do it a little differently. Even though they have many, many differences, each of the presidents of forward land and backward land, they both have a deep love of trains. So they want to do the treaty signing ceremony on a train that is going right across the border.
Predicted it. Yeah. It's just too stupid. Yes, so light, unlike anything else you could put in the train, okay, that's going to get pushed by the air or pushed by some other thing and being caused to move with the same velocity, light won't be influenced. Now, you could argue, frankly, that the light is traveling through the air, and the air is a medium, and the medium is retarding the light a little bit, so it, But yeah, I don't know if it can make enough. There won't be enough change in the density of the air. As the train accelerates, it's going to change the density of the air. There's going to be more air in the back of the train than in the front of the train.
between forward land and backward land. So they set up the same scenario, and here they are on the train. Train is going along. There is a table again in one of the cars. The presidents are equidistant on the train from the bulb. The bulb will be turned on just as in the previous case, and when each president sees the light, he will sign the treaty. Okay, so here we go. The bulb goes off, the light flashes, goes toward each of the presidents, and they sign the treaty, and everybody on the train is again very, very happy with the result. But here's the...
So it all depends on how you think this light can be created. So the faster this train goes, the more the problem is going to be is how do you even emit the light? Because the light emitter, okay, is taking time. So if you think light just instantaneously pops off of a surface, it's just an instantaneous event, and all of a sudden there's a frequency in space, so it just poof into space in an instant. Or you have to understand that no, antennas are kind of telling you that light's a process. So as the electricity moves, it's creating energy at different times, little clumps of energy. So at the bottom it creates a clump and it's on its way, and then there's another clump and it's on its way, and then there's another clump on its way, and that is the frequency, and that is the polarization that eventually you're going to call a photon. So a photon is that collection of energy. It's not just one clump of energy, it's a pattern of energy, and that's the frequency. So if you understand that, you understand that, well, if I start moving the antenna really fast, then I'm not going to have that distance between clumps. I'm going to screw up that distance between clumps, and I might not have any light at all.
Thing, just after they sign the treaty, word comes that the people on the platform are fighting. They're fighting because those folks from forward land claim that they have been duped. They claim that their president from forward land signed the treaty first. How could they come to that conclusion? Well, here's how it goes. So the people from forward land, they are on the platform watching this happen. And from their perspective, look what happens. When the flash goes off, the president of backward land is moving away from the flash from their perspective, so it takes longer to reach him than the president of forward land who's moving toward the flash. So let me show you that again. Watch what happens when the flash goes off. The president of forward land moves toward the flash. The president of backward land moves away from the flash. The light has to travel further to reach the president of backward land than the president of forward land. It has the same speed. The speed of light is constant. So if it has to travel further, it's going to take longer to get there from the perspective of those people watching on the platform.
Right. So the people watching on the platform aren't seeing, okay, any of that because they can't see the light obviously moving. But the fact is that that's all an illusion. They can't change the facts. And just like you can't change what the atom is by moving closer to one piece of it, you don't change the atom, you just change your perspective.
And therefore they claim that the two presidents did not sign at the same moment. They claim that the president of forward land signed the treaty first. Let me show you one more variation on that so you can really see the detail of what's going on.
So yeah, just show me one more time, but don't show the pen actually hitting the paper. Because if you show the pen hitting the paper, it did happen at the same time.
On. This time I'm going to draw a line where the flash takes place. There's where the flash took place. Look how far the light has to travel to reach the president of forward land versus backward land. It only has to travel this distance to reach forward land. It has to travel this distance to reach the president of backward land. Light travels at the same speed. If it has to travel further, it's going to take longer to get there. So we now have an interesting situation. Those people on the train are absolutely convinced that the two presidents signed at the same moment. Those people on the platform are just as convinced.
Okay, so they're just as convinced, even though you showed them the actual pen hitting the paper at exactly the same time. So the fact is they can't see the hand hitting the paper at anything other than the same time because the light message change. Well, you could argue, I mean, they're seeing the one guy later. Okay, they're not seeing the two people at the same time. So yeah, obviously they're seeing the one guy sooner than they're seeing the other guy. So yeah, you can't use the pen argument either. All right, so there's no way to fix it except through understanding it. You understand, okay, that there's a different distance and that it takes time for the information to get to you. That's the simple explanation.
That they did not sign at the same moment. So the big question is, who is right and who is wrong? And the answer is, they are both right. The reasoning of each group of individuals is absolutely impeccable.
Okay, so this would be the same thing as the argument I'm making about the exploding white bomb versus the black bomb. And all he's saying is because you know your perspective is not necessarily neutral, it's perfectly reasonable for the people standing next to the white bomb to say there was more energy in the white bomb because they're whiter. And the people next to the black bomb have to say, they are perfectly reasonable in saying the black bomb has more energy because they've got so much more black on them. It's not really reasonable for them to say it, okay, as a fact. Because, again, we know that's from the third perspective of looking at both of the viewers, both of the other witnesses, we can see that they're biased. So we know that bias can exist, so why are we pretending it doesn't exist? We can know the right answer. We just create the third person.
For those on the train, the presidents are equidistant from the bulb. Bulb lights up. The light travels the same distance to each, so they sign at the same moment. Perfect reasoning. Those on the platform, they say the flash goes off, and it doesn't have to travel as far to President.
So again, there's no point in arguing it that everybody's perspective has a bias built into it, and the obviously the closer perspective, that is the ones on the train, are the better witnesses. So you could just say the further away you are from the event, the less good you are as a witness to what actually happened in the event. So just make it that simple.
Forward land as it does to the president of backward land. Speed of light is constant, and therefore they do not get the flash at the same moment. That reasoning is absolutely impeccable. So what this is telling us...
So they keep telling us, they keep using this exaggerated language that's impeccable to say that your bias is ununderstandable, and it's clearly understandable.
Is that the constant nature of the speed of light means that events which take place at the same time from the perspective of one group of individuals will not take place at the same time from the perspective of another group of individuals moving with respect to them. Now, this relies, of course, on the constant speed of light, because what Newton would have said is he would say the projectile, say the light, will get an additional kick from the train moving in this direction, and that...
All right, so I'm not sure Newton would say that. So again, that's just him speculating that because Newton called light corpuscles, that he thought you could give the corpuscles momentum, more momentum. They're obviously already moving corpuscles. Whether or not they could come at any variable speed or have a variable amount of intensity based on how fast you project them, I don't think was an argument Newton made. So you can try to put those words in his mouth, but I don't think they belong there.
Additional speed will allow it to cover this distance in the same amount of time. The light...
I think Newton understood the inverse square law to mean that you're increasing the density of the particles, not you're increasing the speed of the particles.
Going this way would have its speed diminished, and therefore it's traveling a shorter distance. And when you take those two effects into account, Newton would say both of the presidents get hit at the same time, regardless of your vantage point. But because of the constancy of the speed of light, we come to a very different conclusion. This is what's known as the relativity of simultaneity, and is one of the most startling implications of the constant nature.
All right, so I can tell you, show me some evidence that Newton actually did this thought experiment and come up with that conclusion. You just made that up.
Of light speed. The relativity of simultaneity strongly hints, in fact almost necessarily requires, that motion, speed, must be affecting time itself. The rate at which time passes must be affected by motion. That's the only way that we really can conclude, as we have already, that simultaneity depends upon your perspective.
So it really, what does this have to do with it? Again, you don't need to break the entire universe to explain why people see things differently. And that's what they're doing. They're saying we have to break the entire universe. We have to break all notions of a continuous time throughout the universe. That it's this time, whatever the time is here, I can go a zillion miles away, and it's the same time there, okay? And time is counted the same way, and distances are the same size there. A pencil is the same length over there, too. Everything is the same over there. There's no difference. I don't have to break the whole continuity of the universe to explain that if, you're standing next to the white bomb, you're going to get more white on you.
I mean, in the treaty signing ceremony, if clocks on board the train agreed with clocks on the platform, then everyone would agree on what happens at a given moment. Everyone would agree on whether the president signed at the same moment. But they don't agree. And so clocks that are moving relative to each other must tick off time differently.
So again, they're not ticking off time differently. So And the only argument to be made is that you can break clocks. So yes, you can give a clock velocity and break it. But in that case, both clocks have the same velocity. So in that case, it wouldn't matter.
Now, for us to make that idea precise, to us to really understand how it is that motion affects the passage of time, we need a way of measuring the passage of time. We need, of course, a clock, right? Now, you can use, for all that we are talking about here in relativity, you should feel free to use any clock that you like, right? Your favorite Rolex, your favorite grandfather clock, any clock that you'd like to use. I, however, am going to make use of a special kind of clock that's quite unfamiliar, but as you will see, it's a very powerful kind of clock for assessing the effect of motion on time.
Right, so this is where you get into the light clock crap. Okay, so let's see what time we are. We're over an hour, and we don't have any comments. So yeah, we'll just call this a video, and be back at some other time to finish this. He's probably going to jump to another chapter here, so I guess I might as well play it out until he jumps.
So I should spend just a moment addressing the issue of
The light clock.
What is a clock, right? So what is a clock? A clock is any physical system that undergoes cyclical repetitive motion, and it does that cyclical motion. It undergoes those cycles in a uniform way, right? So if you're talking about using the Earth as a clock, the Earth spins around its axis in a uniform...
So understand what I would make as a premised argument is all the clocks are based on the speed of light. All the clocks run on a force that has motion at the speed of light. So all the clocks are some variation on a clock that directly would measure the speed of light. So the light clock would just be the most direct version of a clock, the most unbreakable clock, and all the other clocks are just a constant, or just an emergent function that takes place based on a force moving the speed of light, causing an effect. So every other clock is just a consequence of the speed of light.
way, and we use that to say every time it goes around once, it's a day. We can talk about the Earth in revolution around the sun, right? It does that in a fairly uniform, cyclical way, and we call each revolution a year. And on a more standard wristwatch, if you have, well, I should say one of the old-fashioned ones that has a second hand that's sweeping around, it does that sweeping motion cyclically, sweep after sweep after sweep, and we call each of those sweeps a minute, right? So that is what...
No, what you're really doing is pushing matter with a spring, okay? And so you're relying on, like in some of those old, tick, 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 clocks. That's what you're relying on. And then a crystal clock is just using a crystal's frequency of vibration that's even more consistent than a spring's vibration.
Clock is, conceptually. The new kind of clock that I'm going to introduce has that same kind of feature. Cyclical motion, a cyclical process happens over and over again, but the process itself is a little unfamiliar because the kind of clock that I'm talking about is called a light clock. What is a light clock? A light clock is a contraption in which we have two mirrors that are facing one another, and a ball of light will bounce in between them. And every time...
All right, so the ball of light, again, as I'm stating, you can't create it as a ball of light. You have to create it as pieces of light. And so each piece has to have a different time that it's created. So when you move the emitter, you're going to change what you've emitted. Okay, and the same laws are for the receiver. If the receiver's moving, it's going to spread the light. If the target's moving, you're not going to get all of the arrow to hit the same place. Yeah. Anyway, all right. So we'll just call it a video here. All right. So till the next time and such, so forth and whatnot. Clean that up. Probably should have some simulation to show you in the next video, but see how it goes. Pretty close to illustrating the basic functions. Anyway, I don't have to get rid of it, but I might as well because there's nothing in it. Let me just go to the actual live thing to make sure there's no comments, which, really is kind of irritating. Hey, the little logo's missing. Huh, that's unusual. Usually you can pop it back in, and there's no there's no pop it back in option. Huh. Alright, well, let's close it then. We'll see what happens. Alright, there. Alright, so there's nothing there. We'll make sure it's top chat is just so stupid. Yeah, I want the live chat. Thank you. All right, anyway. 23 viewers and nobody comments. Interesting. Okay, well, anyway. It's the internet. Alright, so till the next time and such and so forth and whatnot. I don't need that anymore. And I just get the hell out of here. Alright. Yeah, so goodbye. Yeah, I'm fading. I'm fading. A cruel world. All my power is gone. Blah, blah,